Arjumand Yakub is from Qualcomm Incorporated, and he's going to be presenting remotely and talking about the deploying AI in DV for smarter and faster IP verification. He holds a bachelor's and master's degrees in electronics engineering and brings extensive experience from leading technology companies, including Qualcomm and Intel. Currently based in San Diego, California, Arjumand works as a staff engineer, focusing on advanced design and verification solutions. Okay, so we're going to start now, and I'll start with the first few slides. And we're talking about deploying AI in DV for faster and smarter IP verification. We're going to focus on IP verification here, although we've done this for SoC verification as well. Okay. And that's not going to work. Okay. Okay. So the abstract for this talk is that AI is set to, as we've heard a lot today, AI is set to play a key role in optimizing the traditional design verification flows and challenges, providing a faster and smarter platform to deploy and use in design verification while verifying designs of different complexities. And we've applied this to some simple designs and very complex designs. And we've got an AI strategy and model. Okay. We'll apply that to generate a verification environment. So we're going to show you how we generate our UVM test benches and then how we try to generate the test cases separately and try to say we're going to apply it to IP verification here. Okay. So the outline is we're going to talk about AI strategy. We're going to talk about UVM test generation. We're going to look at some results and analysis, the models and techniques we're using, the features that we've implemented, and then we'll talk. We'll show you the conclusions that we've developed from all of this work. Okay. So this is the way we work it here is that we take the IP design separately. Quite often, rather than using the actual IP design itself, now we're using configs, the specifications only, because obviously you don't really want to pull the RTL in too much into your verification solution. So now working mainly with specifications or config files. Okay. The AI model then has a training data to allow us to train that AI model. And that allows us then to develop an automated UVM test bench. And then we've got a feedback loop that says, with this test input data, this is the coverage score that we achieved. And we then feed that back as verification constraints into the AI model. We get an updated test bench, and then we're able to run again. And we generate a lot of stimulus from that. Okay, and then the generated stimulus that actually get the highest coverage can be separately saved. Okay, so the RTL and specs are extracted as input. Okay, regression testing is based on building the ML model with test and random data as input layer that results in outputs and coverage bins. And the failure signature as well. So obviously what we're getting out mainly are two main outputs. One is the failures, and we've heard a lot about failure signatures and how you can do debug based on failure signatures, but also get the coverage bins, which allows us to try and close coverage a lot more quickly. Okay. The pre-trained model based on data collection, feature extraction, the model training, and the deployment. Okay. We have bootstrapped with historical results as well, and then every time Gen AI does a new release, we just replace our model and retrain it with the previous the previous stored data, so we can retrain models very, very quickly every time Gen AI or ChatGPT does a new model release. Okay, and so if we look at this here, we've got these AI models, the tests with a choice of sequence length as well, because a lot of people today have talked about long tests, short tests, etc. So we do allow the AI model to we give it information about how long a test we want. Whether we want lots of short tests or a few longer tests, and that allows us to control the simulation time. So if we've got lots of simulators, we may want to choose lots of short tests. If you've got an emulator or a couple of emulators, you may want to choose long sequence lengths. Okay, and we've got a feedback process going on there. Okay, and then the effectively AI model is giving us the parameters that allow us to control the test generator. Okay, and so that test generator then is separated from that AI model, and the connection is through these parameters that we set up. Okay, and the outcome is that we can we try to close the coverage and with a higher percentage, but with fewer tests. Okay, now at this point, I'm going to push the technology out and ask Arjuman to become the presenter.
Yeah, so thanks. So basically, as Mike has explained about the different strategy inputs and the high level models as he has shown in the previous slide, basically what I'm going to explain here in these couple of slides is basically a kind of practical model that will show you how the coverage feedback model has been implemented, and basically it takes the model feedback from the coverage score and basically um, update the stimulus and that how the stimulus is gonna run on the upcoming iterations for the coverage flow year, and it basically optimizes the runs where we are basically running a different set of tests and sequences, and it basically gets trained on the way through the model, and basically it improves the whole coverage closure cycle with respect to the time, run time, and the score and the quality. So we can go to the next slide.
Okay, let me just so coverage closure flow, correct?
Yeah. Yeah, so basically, this will show you the flow where we were talking about based on the strategy inputs and the model we had. So it will show you how we basically have a start from the specs, and basically we basically set the test pen generated through the Python generator model, which will I'm going to show you in the next few slides, and then basically we have the simulations going on from the test bench is running, and basically the all the regression results are generated and basically being optimized by the by how we are constraining those. But the most important thing here is to show you like the how the coverage is basically being optimized from the coverage scores that we measure after each set of iteration of the regression runs, and it basically controls how we are going to feed the next set of regression data and for the next set of iterations. So if we go for the complete flow diagram now, here it will basically show you that how we are actually uh, gauging and measuring the goals, verification goal in terms of the coverage, and basically optimizing it with our with our feedback on the next iterations and runs, so that it basically gives the optimized result for the next time and the most targeted results for the and run only those simulations which basically are adding to the most coverage results. So in this whole model, it basically shows you different key things where basically we have the input, the model strategy implemented in terms of like the coverage feedback, and also the main part where we have the automated test pen generated, and with in terms of like the integration of different techniques where we basically have combined those to actually form that complete model, which basically have the automatic test bench and the coverage feedback flow implemented. So we can go to the next slide. Yeah.
Okay.
So in the next slide, basically, what I'm going to show in more detail is about the automated test bench. It basically like the Python generated test bench for the UVM, and it is the part of that model that incorporates the whole modeling and the strategy that was shown earlier. So it's basically the one of the integral part of that flow where we have the test bench automation implemented, and we basically read the design specs and interfaces and the configurations and generate a UVM based standard UVM based test bench, which basically is the main test bench, which is actually generating all the stimulus and driving all the traffic for a particular IP or design in question at the moment. So it shows you like this slide shows you like the high level block diagram, how it has been implemented. I mean the extraction of the specs and the signals and the configuration, and as an output it has a test UVM test bench. So we can go to the next slide where we can show you of some more detail about the inputs and the outputs from this generator. So basically, this is generator is reading the I/O interfaces and the design from a .sv file, and basically also some extra configurations in terms of like which basically explaining that how the design specs and behaviors are implemented, and based on all this knowledge, this model basically is going to generate the test bench as an output, where it basically have the sequences and all the related infrastructure for a UVM standard UVM test bench, which basically can run uh, all the simulations can be run based on the test cases we have. So it's going to generate based on these inputs, it's going to generate the UVM test bench output. So we can go to the next slide where we can see that as an output, basically we will have the an example UVM test bench generated, where we have all the standard file and all the standard infrastructure needed for this test bench uh, for for any design under basically test. And the next slide, if you go, it will show you the a kind of a graphical representation of how the test bench would be look like, which is like the automatically generated and basically will be deployed to generate the stimulus. So yeah, so if you go to the next slide, so basically that's like the main part, one of the main part from this input model, which has been incorporated, is this test bench automation, which will help a lot of time saving and improvement in the accuracy and generation of the stimulus. Basically, that incorporates through this model, and it becomes the part of that complete model, which is deploying the AI strategy uh, for the complete input taking into consideration one input model and deployment of that for the complete verification cycle. So that basically the test bench automation, which is one part of that, is basically doing this optimization on this end, and it's basically becoming the part of our optimization and verification. So if you go to the next slide, Mike, where I think we are going to summarize in few slides that how this AI strategy model and techniques are basically have been taken into care, and how we are used to optimize them and develop a model that has been shown in terms of like coverage, closure, and the verification goals uh, have been met through the implementation of these techniques. So I think if you want to go over those, you can I can hand over to you, and you can finish uh, in these few couple of slides.
Okay. So I'll finish off here. So the objectives really here are to increase verification efficiency, improve test coverage, but bug detection and debug time as well. Try and doing the debug time back by providing information about the types of failures that are in there. We're using supervised learning, learning from input and output pairs and look at failure patterns. We've used unsupervised learning, reinforcement learning, and optimize test sequences via reward feedback. So we tried all these different techniques. We work with quite a few different partners and local universities in the UK and India on this. So we've been working with lots of different partners. So we've got an enhanced verification pipeline. We do try to predict failures and coverage bins. So this is based on some work we did with Infineon, where they rather than necessarily always run a set of tests through the model, they can we've got a model that will try to predict what coverage those tests will give, and then start to pre-select, and then run, and then just run a subset of the generated ones, the ones that they think will give the highest coverage, and then you can make sure that your prediction, when you've actually run those tests and got the real coverage information, you can look at whether your how accurate that prediction was, so you can continuously learn about your predictions, and that does save a lot of time. So you don't have to keep running everything through simulation. You can run it through your prediction engine and then see how good your predictions are. Okay. Neural linguistic programming, smart regression, GNNs, and AI-driven debug. Okay. And our model training data as the input layer is typically, this is in the model itself, generating the test and random stimulus, and the output layer gets its feedback from the coverage bins and the failure signatures. Okay, and that's how we train our whole model, slightly different for the input layer and the output layer. Okay, in our training process. Okay. And then the bug isolation. So although you may get lots of, 100 failures, 100 failures may only be due to 5 bugs. And what we try to do then is to try and look at the signatures of those failures and then put them into different sort of buckets for each bug type. And then you may end up with those 5 bug types. And then within your bucket, you can choose the shortest simulation length to try and accelerate your debug. So that's how we try to accelerate debug, by putting all the failures into, to the minimum number of buckets, and then give you the shortest simulation per bucket to debug. Okay, I'll skip that one. So we've looked at UVM test bench automation. Again, we use Python as well as AI there. So there's a blend of Python and AI, which we think gives the most efficient solution. Okay. And as I talked about, we do bug isolation, test plan creation. We can do a test plan creation from the PDF, the specification or requirements. We can generate the test plan, and that will just mainly look at what the coverage is, and what features does the feature extraction, and then generates a coverage plan based on that feature extraction. Okay, we looked at bug prediction and root cause analysis. And okay, we also generate high reference models, higher level reference models, which we typically use in our scoreboards when we do that UVM test bench generation. Constraint optimization from the feedback loop as well. Okay, so we have seen a reduction in the manual time. So as I say, typically we can actually see a 90% reduction in effort on that UVM test bench generation, and we've measured that across about 5 different projects, and getting consistent results on that. The proposed model and infrastructure can be augmented with more AI-assisted tools, so we can bolt in new AI-assisted tools very, very quickly. We use it for both feature extraction and coverage tuning, that should say, rather than tanning. But it's a so we do the feature extraction at one end, and we can then do the coverage tuning at the other end. We use automation for test bench. We can also apply that to UVC, so it's not just a test bench for a piece of IP. We can generate a UVC and structure it as a UVC rather than a test bench with different sequences and tests. And we will fine tune it using machine learning based on the analysis of the following, the results, the debug data, and regression data. And there's a reference there, and you can pick that up afterwards if you want as well. Okay. So thank you very much. At the end of this session, if there's any questions, we can take them now from the audience. Otherwise, we will just very, very, very quickly do the closing slides, and we'll close up in here, and we will. Okay, so I will quickly go into here. Okay, and hopefully this is now working, which is good. So thank you again for participating today. I hope you've had an enjoyable day and found something very useful, either in the presentations or the networking or the booths. And we do encourage you still to look at the booths. I think they may still be out there. Some have packed up and gone early, but I think some have maybe stayed to the end. Cadence, Doulos, Real Intent, Synopsis were a platinum speaker today as well. And there's some of the startups ones there that you can see, Lubis, Moore's Lab and Bronco, Moore's Lab and Bronco, who are startups. And I myself, Alpine and consulting as well, working very closely with TestSolve in this conference. And there's a list of that. And again, Synopsis were our platinum sponsor for today. That's why you saw a couple of presentations from Synopsis. Everybody else just had the one. Everything will be on the Verification Futures TestSolve website, 2020-25 Austin. You'll get a link to that. You'll see the PDFs of the PPTs, and then you'll get the videos as well. Okay. And remember, if you've got anything that you want for future, just send your ideas to verificationfutures@testsolve.com. That's an alias. A few of us will get that, and then take your ideas on board as well. Just for 2026, definitely in the UK, and I think we've really got a date for that. And we got our usual university booked. Austin is confirmed. We will be back here in 2026, and the Silicon Valley is very, very likely. We're just trying to find the right venue and the right costs and the right sponsors for that, and the right themes as well. There may be a test track as well there, so we may be expanding and bringing in a test stream as well. And when I say test, I mean manufacturing test there. Okay, and that should be it. Just a bit about our Python, which I'll flash through quickly. And we're finished there. Thank you. And safe journey home. And hopefully we'll see you all next year, plus some others as well. So thank you very much for attending today. Thank you. And thank you to our helpers as well. Thank you. Okay.